I will give a bit presentation on a bit of theoretical aspect, and in particular on the polarization and how it depends on the collision frequencies when we see a meteor. This topic sounds a bit theoretical, and it actually is, but let me a bit motivate the whole story. From the visual, you know, in the left upper part, how a meteor looks, and now we want to look at the radar part. And we want to understand what we are actually observing. What is the physics behind what signal we get back, and how is the signal generated when the radar scatters off these plasma trails. And the key thing here is that the basic principles are known since the end of the Second World War, but quantitative calculations turn out to be very, very difficult. And I will come to this part a bit in this talk, but I only briefly go through the equations. When we look at the echoes that we can see with a radar, we have basically three types, which are shown in the left panel. And yeah, you have here the head echo at the beginning, which is this very narrow plasma column. It's usually overdense in front or around the meteoroid itself, and it travels at the same speed of the meteoroid. And this is in the Rayleigh regime on this curve. So it is a very, very weak signature. That's why we see much less head echoes than, for example, specular echoes. Specular echoes, this is the key thing of this talk. They are in the optical regime and occur when the radio wave bounces off perpendicular from the meteor trail. And we have also non-specular trails, but this is a different physical process of the scattering and will be not covered too much in this talk. When we go back to the classical theory, and every radar meteor scientist knows about this corner spiral and about the theory that was presented in McKinley in the very famous book, which actually goes back to the Kaiser theory of 1953. When you look at these equations, you know that the signal morphology is basically described by a modulation from the corner spiral, which are these integrals here denoted as C and S, or F square and with a cosine and sine function. And all the other parts in the equation are basically radar constants: power, antenna gains, wavelength, and this magic factor Q here. And when we want to describe the diffusion and the decay of the meteor, we always assume, oh, let's put an exponential decay to this equation, and the signal fades out. Which sounds very reasonable, and it gives a nice representation of what we actually observe. The problem is this Q doesn't change. So damping the Q exponentially is not what physically is happening. And it's also clear that the radar parameters are not exponentially dampening while we're taking the measurement. So there is a problem here. And this is a bit what we try to solve with a theory. And this is done with a full wave scattering model. And I will not bother you too much about this, but the main principle is that we now try from a first principle solution from the Maxwell equation to attack this issue. And Maxwell equation, I guess everyone has known them, or at least seen, and one can derive with a simple assumption about a cylindrical geometry, so that the plasma is radial diffusing in the trail. We can get a set of equations, which is shown here. And this set of equations in cylindrical coordinates can separate two fields, the electric field and the magnetic field, and both can be swapped for symmetrical reasons in the Maxwell equation. And as you can see, these equations look not the same, but they are supposed to look the same. And the second big thing is that when we have a plasma, we are not in free space. We have a complex permittivity function, where we have here our plasma density, which actually contains also all the chemistry of the trail, and we have collision frequencies. So how frequent our electrons and ions that we release from the meteor are colliding with other objects in the trail or in the ambient atmosphere. And all these things need to be connected somehow. And we also need a plasma model, as we are not scattering off a metal sphere like from a solid target. We are actually scattering of a distribution. And these distributions can look quite different. The analytical solution for a cylindrical diffusion equation is given by a Gaussian function up here. And this is also the one where all the results that I will show are based on. And it nicely assembles this model here, which is called the Diamant and Oppenheim model, which is also obtained from 3D plasma simulations on a supercomputer. And you see the differences are so small that it is reasonable to work with the analytical solution for the plasma. And we also have the ability to use incurrent scatter radars to get an idea of collision frequencies, in particular of the ion-neutral collision frequency. This is the one that dominates how fast the trail expands in time. And we also see that this frequency changes quite a lot with altitude. We are talking about almost 2 orders of magnitude. So in these changes on the collision frequency is only one part. So this is for the diffusion of the heavy part, but we have also electron-electron collisions, electron-neutral collisions, and electron-ion collisions. In particular, the electron-ion collisions, these were the ones that were excluded in Kaiser's theory. They were not included at the time. And this is equivalent, if you do not include them, to assume that the electron and ion temperatures are always in thermal equilibrium to the ambient atmosphere. And we will see, unfortunately, this seems to be not always the case. And we did test the theory by taking measurements with the SAAMER orbital system in Argentina, Rio Grande. The system is a multi-static system with 3 outlying receiver stations here, and the core station, which is a classical monostatic meteor radar. And the system allows for precise orbit determination, time of flight velocity. So we have all the information about the trajectories, and we added another antenna for polarization measurements. The transmitter, and this here it's still shown as a transmitting array. We only transmitted for this experiment with a single antenna, about 60 kilowatt. And the reception is done in the Jones array, shown here, and with 2 separate receivers on the polarization antenna. So in total, we obtain circular polarized signals from the core array and linear polarization signals from our 2 polarization planes, which gives us 3 conditions. And we actually can now fit our model to the 3 conditions. In the upper panel of this figure, you see the circular polarized signal averaged over the main array. The blue part is a measurement calibrated with a noise generator. Black is noise generator, blue is a cosmic noise background, and the red one is the full wave scattering solution for this meteor trail after the fitting. And we can also go further and say, okay, let's look what Kaiser's theory would state for this type of echo. And I don't want to do too much of the details, but the basic idea was when you can measure the time, how fast your signal decays to half the power. And this is a measure of the ambipolar diffusion. And basically, this is well known. This is the standard technique that is applied in all the data analysis I have seen so far. And it's also done in very much in all the temperature estimates for the atmosphere with meteor radars. And we have the full wave scatter solution, where we already know this. We know from our fit exactly these parameters. And now the idea was, okay, let's apply Kaiser's theory to the full wave scatter model. And we can even remove the Fresnel oscillations because we don't need them. This is just the convolving part. And we can express the differences between both solutions as a difference of these electron and ion temperatures, which were always supposed in the past as to be equal. And guess what? You see differences. The bluish part is actually the good news. This is where Kaiser's theory fully holds, and we can assume that both the signal morphology follows this exponential decay as the classical analysis shows. However, when we go up to higher frequency in the collisions, you see that this threshold goes down. And on the left axis, you see these electron line density thresholds. And when you look back in the literature, for the transition between underdense and overdense meteors, we always assumed a threshold of roughly 10 to the power to 14. However, this number was obtained far high up. The collisions that we put in here are around 100 to 110 kilometers. but we see the vast majority of meteors further down. And if you calculate this into collision frequencies, you go down with the threshold. And in principle, everything above the white line is a kind of transition echo where the assumptions of neglecting the electron-ion collisions doesn't hold anymore. And when you now do some initial statistics about many of these echoes, you can get actually from the full wave scatter solution nice vertical profiles. And you have a new type of echo, which is called a transition type of echo. This shows signs of resonance effects in the polarizations, which were not accounted in Kaiser's theory, but you still can get a good solution for the diffusion profile, initial radiators, and also for the line densities. Yeah, I'm done. And yeah, and in short summary, also we can use the polarization observations to replace the complexity of using triple frequency observations. Triple frequency observations would mean 3 identical sets of radars with a spacing of 10 megahertz and more, which would be very expensive. Or use 1 antenna with 2 polarization, 2 receivers, and you have the same. It's equivalent. And we can account for these issues that follow up. We get much more reliable electron line density measurements. This will improve our mass estimates, and the deviations are huge, much larger than you would expect from these TE ratios. And it's also now possible to go further on and try to automate the whole pipeline so that you get routine and large statistical analysis, which will also help to get more reliable atmospheric parameters from this model approach. Yeah, thank you.